We're now going to take a look at the solution to this question reported earlier. The question, what is the energy of 1 mole of photons of red light with a wavelength of 725 nanometers? We're first going to look at the stem of the question, that is just the written question sentence itself, and try to identify any equations and or relationships that might be helpful to us in generating a solution. We see a reference to the energy of photons. And I seem to remember an equation where the energy of 1 photon of electromagnetic radiation is equal to h, that's Planck's constant, 6.626 times 10 to the negative 34 joule seconds, times the frequency given by Greek letter nu. And the units of frequency are seconds to the negative 1, also known as hertz. We also see a reference to wavelength in the question. Now, there is no wavelength variable in this energy of photon equation. However, there's another equation that we learned about where c, the velocity of light in a vacuum, 2.998 times 10 to the 8 meters per second, is equal to the product of wavelength in meters times the frequency, which is again in seconds to the negative 1, or also called a hertz. Now, there is no equation that actually unifies energy with wavelength, which is exactly what this question is asking us to do. So here's a great little hack that'll help you solve this question in half the amount of time. Rather than having to solve for a number, plug it into another equation after you've solved it, let's note that in this equation for speed of light and frequency, I can divide both sides of the equation by lambda, so that nu is equal to c divided by lambda. If c divided by lambda equals nu, I can then substitute c over lambda back into this equation for the energy of a photon. So now if I substitute c over lambda for nu, I come up with this one-stop shopping equation where the energy of a photon is equal to h times c divided by lambda. So that right away cuts your problem-solving time in half. Before we jump right in, however, let's note a small discrepancy. We're told, as we typically are, that the wavelength of this photon of visible light is in nanometers. This mismatches the distance units of meters in the velocity of light term. As an important rule of thumb, whenever you're solving a problem that involves a constant, whether it's Planck's constant or speed of light, or whether it's the capital R in the ideal gas equation, the units for the values given in the equation need to match the units in the constant you're using. So first, before we do anything serious with this, we have to do a little bit of housekeeping. That is, we have to convert the 725 nanometers into meters so that the distance units of meters match the distance units in the c term that we're going to be using when we ultimately plug our numbers into this equation that we have at the top of the screen here. I then take my 725 nanometers, I multiply this by 1 meter divided by 1 times 10 to the 9 nanometers, which then gives me 7.25 times 10 to the minus 7 meters. This then cancels out the meters so that we're left with units that we can use and we know will cancel out with our c. Now we can get serious, roll up our sleeves, solve the question. I'm going to go right ahead now and plug in the Planck constant, multiply this by the velocity of light in a vacuum, and now divide by my new and improved wavelength in units of meters. In so doing, you can see how the seconds units in the Planck constant cancel with the seconds units in the velocity term. Also canceling, as we had planned, are the distance units of meters in the wavelength with the distance units of meters in the velocity of light term. This gives us this unrounded answer of 2.73996524 times 10 to the negative 19 joule per photon. We're not done with this question, which is why I have this apparently superfluous number of significant figures. Why are we not done? Because this number and these units don't match the units of the choices given in the question. Let me show you what I'm talking about. So all these units that you see here are given in kilojoule per mole of photons. Well, this is only the joule of the energy quantity of one photon. Watch out for this. Notice how the magnitude of the energy per photon that we just calculate matches the magnitude of the energy in choice A. This is a fantastic way to trap students who are just plugging and chugging along but aren't paying attention to units as they're doing their calculations. And it's the first choice too, which is, as I say, it's a fantastic way to ensnare people who aren't paying attention to units and are just trying to, I guess, hopefully get the problem done. So the magnitude of the answer is the same, but the units don't match. So we need to get the units to match. The way we do this is, because we have the energy of one photon in joules, we have to convert the joules per photon that we calculated into kilojoules so that we have a value that's going to match the choices that we were given. What's more, we were not asked what is the energy of one photon, but 1 mole of photons. So whenever we have to amplify a quantity by 1 mole, we have to multiply it by Avogadro's number, because each of these choices asks for the energy of 1 mole of photons, not 1 photon. And so we just have some cosmetic changes we have to make, but important cosmetic changes. Here is my unrounded energy in joules per 1 photon. I'm going to multiply by 1 kilojoule of energy, contains 1,000 joules of energy. And because I want to know 1 mole of photons, I'm going to multiply 6.022 times 10 to the 23rd photons per 1 mole of photons. This then cancels out my joules as well as my photons, giving me the units that are in all the choices of this question, the kilojoule energy quantity of 1 mole of photons. That value turns out to be 1.65 times 10 to the 2 kilojoule per mole. Now I have the correct number of significant figures because this is my final answer, and this matches choice C.